This video is on organic chemistry, IGCSE. We'll start by discussing petroleum. So petroleum, a fossil fuel. Petroleum is mostly made of carbons and hydrogens. Any organic compounds that are made of only carbons and hydrogens, we call them hydrocarbons. So petroleum is a mixture of hydrocarbons. But if an organic compound contains carbons, hydrogens, and oxygens, then it's not a hydrocarbon, but it's still an organic compound. Petroleum is made from the remains of dead organisms that fell to the ocean floor. So it takes a very, very long time for petroleum to be formed. Therefore, it's non-renewable. If we were to use it too fast, then our next generation might not be able to enjoy having petroleum. Same goes for natural gas and coal, and all these are all non-renewable resources. We should use it sparingly. Natural gas is mainly methane, and coal is the remain of lush vegetation that grew in ancient swamps. Methane is the most simple alkane. It is made of one carbon and 4 hydrogens. If you followed some of my earlier videos, I might have already told you that carbons should always have 4 bonds and hydrogens should have 1 bond. So this is what methane looks like. Let's look at other hydrocarbons. For example, if I were to write this CH3, CH2, CH2, CH3, the way to present this is called structural formula. And the way I presented this just now, the methane, this is a full structure or a displayed structure or a displayed formula. So we can present it in a few different ways. We need to know both for IGCSE. The molecular formula for this CH3, CH2, CH2, CH3 would be C4H10. So we can draw a straight chain like this. I'm going to draw a displayed or full structure here for exactly this. So it's a butane. So if we look at this, there's a CH3 here. So CH3, CH2, that's CH2, CH2 again, CH2, and CH3, that's CH3. I can change the position and make it a branch chain. And I'm going to draw the full structure again. This is my branched chain. That is a methyl propane. And if I want to change it to a structural formula, the way to present it, I can. We're going to do what we did just now. So CH3, I'm going to write here CH3, CH, and there's a branch here, CH3. If a branch, we'll just put a bracket here, CH3, and the last CH3. So this is the way to present it in structural formula. There's another video in my collection where I show how to present this organic compounds either in structural or full displayed formula. So you can refer to that. We can refine the petroleum by fractional distillation, and that separates the different compounds that is in the petroleum. For example, there might be some methane, ethane, or propane, or the heavier alkanes. And the heavier or larger the molecule gets, the more viscous it will become. So going down this homologous series, it becomes more and more viscous. This is because it has stronger intermolecular forces as the number of electrons increase. What do I mean by that? So for example, we had the alkane, the methane up here. There's 1 carbon and 4 hydrogens. And the next would be ethane. Obviously, the ethane would have more electrons, so stronger London forces or intermolecular forces. And as compared to, say, hexane, that's 6 carbons, this would have even more electrons, which makes its intermolecular forces even stronger. Therefore, it's more viscous. So if we look at the boiling points, up to 100 degrees Celsius, it's very runny. It's not so viscous. It's volatile. And how easily does it burn? It burns very, very easily. The size of the molecule is small. So small molecules like this. And the next fraction, say from 100 to 150 degrees Celsius boiling points, it's still runny. It's less volatile than the portion before that. And it also burns easily, not as easily as the fraction, the first fraction there. And it's slightly bigger. And as you go down, you have this range, 200 to 300 is viscous, as in it's thicker and more sticky. This is not as volatile. And how easily it burns? Only with a wick. And molecules are larger. Different fractions of this fractional distillation, they have different uses. So this is a list of what are their uses for each of these fraction. So 1 carbon to 4 carbons, these are very light, like methane, ethane, propane, butane. These are used for cooking, for heating, and slightly heavier than that, C5 to C6, they are our car fuels. Naphtha, the next one, hexane onwards. They're starting points or feedstock for many chemicals and plastic. So we use hexane up to this C10 to make plastics and so on. Fractional distillation is to separate these fractions. But for example, if there's an abundance of naphtha, there's a lot of naphtha, and we don't have enough material for cooking and heating. So we can break this C6 to C10 to make it smaller and become C1 to C4. So we might not need as much plastic as we need gas for cooking and heating. So we might want to break this naphtha. Now to do that, we will run cracking. Therefore, cracking has a different function from fractional distillation. Cracking is one of a thermal decomposition reaction. What is this thermal decomposition? Thermal decomposition means, let's look at the equation here. It means that if you have one reactant here and you apply heat to this, it forms a few products, which means I didn't add A plus B and it became something else. It's just one reactant and it became a few things. That's a thermal decomposition reaction. That's what cracking is. The example shown here is naphtha. The portion that they took was decane, which is C10H22. It's an alkane with 10 carbons. We saw just now that naphtha is used as starting materials to make plastic. Let's say we don't need so much plastic. We're in an industry which sells gas for heating, or maybe we need more car fuels. We don't need so much plastic. So we want to break this naphtha so that it'll become a smaller carbon chain. In this equation, we see that it becomes 3 different organic compounds here, pentane, propene, and ethene. Now the equation is actually not fixed. So it's not necessary that it has to form pentane, propene, and ethene. In exams, as long as you can balance the equation to 10 carbons and 22 hydrogens, you can draw almost any combination you want. So for example, if I've drawn propane, so I've used up 3 carbons and 8 hydrogens. Okay, I'm going to settle the carbons first. So I'm going to draw maybe another organic compound here, propene, and I have 4 more carbons left. So I'm going to just draw 4 here. I'm not sure if it's going to be a butane or butene. Now let's complete that structure first. And we're going to use 6 hydrogens for propene. Now, how many hydrogens have we used? So 8 plus another 6, so that's 14. Okay, so if there's 14 hydrogens that has already been used up out of 22, so there's 8 more. So I can't make a butane for sure. I'll have to make a butene. You can draw the butene either way you want. You want it to be a but1-ene or but2-ene, that's fine. So I'm going to draw but2-ene. So this equation would make sense as well. It doesn't have to be pentane, propene, ethene. It can be a propane, and butene, but2-ene. Let me just specify that. Or if you want, you can draw a but1-ene instead. Okay, as long as your equation can balance, then that is fine. But if you haven't noticed, it's always the alkene that is more abundant compared to the alkane that is formed. This is because the hydrogen is not enough. When you break this naphtha, there's a gap here, right? So there's not enough hydrogen to form all alkenes. There's bound to be some unsaturated hydrocarbons. When cracking is carried out, the products will always have shorter chains and they are smaller molecules. So smaller molecules means, of course, they're lighter with less electrons, so they have weaker intermolecular forces. They're going to be more volatile or more easily vaporized. So the products are more volatile, smaller, and has shorter carbon chains. Nothing is added, so there's nothing new. It just needs the balance. If you have 10 carbons to begin with, you must have 10 carbons total in your products, right? You have these 3 products here, or these 3 products here. Okay, long chains aren't the only ones that can undergo cracking. Even the shorter chains like ethane, it can undergo cracking as well. Here they applied 800 or more than 800 degrees Celsius, and instead of having an ethane, the product will be an ethene. So you see, the products are more often alkenes than alkenes. And then we have hydrogen here. You might have heard me mentioning homologous series just now. What is this homologous series? So something that is in the same homologous series, or they're in the same family, we call it, the same family of organic compounds, then they will all fit the same general formula. For example, alkanes, their formula is CnH2n plus 2. So we did draw that methane, so C1, I'm not going to write the 1, H4. So 1, 2 times 1 plus 2, that's 4. Ethane, C2H6. So the N would be 2. 2 times the N is 2. That makes 4 plus 2, that's 6. C3H8. So I have 3. 2 times 3, that's 6, 7, 8. So they all fit into this formula. Alkenes is from a different family of organic compounds, so it won't show this CnH2n plus 2. Instead, it's going to show CnH2n. For example, ethene, so C2H4, propene, C3H6, butene, whether it's but1-ene or but2-ene, that's C4H8. So it has a different general formula, which is different from alkanes because it's from a different family, a different homologous series. Going down a homologous series like this, methane, ethane, propane, butane, pentane, hexane, usually each is different from the one before by 1 unit of CH2. For example, methane, CH4, ethane, let me draw that in a structural formula like this. An extra CH2 here, and butane, again, an extra CH2 here. And the next one, yes, you guessed it, just add 1 more CH2 and hexane, 1 more CH2 from the one before it. So this is a homologous series of alkane.